Hi, it's Mr. T here. In this video, I'm going to focus on how we can justify or give explanations to how we identify different functional groups in organic molecules so we can identify what the organic molecule is. This is particularly important if you're doing Achievement Standard 91911 for Level 2 NCEA Chemistry, and if you're doing it in a context of organic chemistry.
If you find this video helpful, don't forget to share, like, and subscribe, and look out for new videos.
Hi, in this video, I'm going to go through how you might set up writing a report for Achievement Standard 91911, that's Chemistry 2.2 NCEA Level 2, identify an unknown species. Now this one specifically is about how to identify organic functional groups or organic molecules present. So usually what's going to happen is you're going to be asked to identify unknown samples. In this case, 3 unknown samples, A, B, and C, have been isolated from a product, a desk cleaner, that was used during the COVID-19 pandemic. Each sample is one of the 6 below. I'll show those to you soon. But what we need to know first is we need to write a short report about these. And in our report, we need to include the following things. We need to give the name and the formula of each of the 3 organic compounds we have identified from the 6. We need a description of how we identified them, that is, what practical tests we did in the lab to identify what the functional groups were and hence what the molecules were. We need to describe the observation, so as well as saying what we did, we describe what we observed, specific color changes or other things we might notice. We need to, if there was a chemical reaction, include the structural formula or the drawn out organic formula and the reagent that is used, and we're also going to draw the structural formula for the product, so for the reactions and the products for the whole reaction. We need to justify why we believe that we've identified the correct group, and we need to use secondary as well as primary observations. Secondary data is stuff like, is something soluble or does it react with litmus or not? Primary is a reaction that occurs that we can write down, and so we need to look at both of those. I'll go through that. And the last thing is we actually have to look at the molecules safety data, and we need to give some advice on whether we think it's appropriate to be used in this scenario that they give us. So in this example, for the desk cleaner, they've said that there are these 6 possible molecules. So we're going to be given 3 unknown samples, and we would go through and write observations for 3 unknown samples. Now what I've done is I've gone through and tested these 3 unknown samples, and I've got a wee animation for a start so we can look at what's happening. Okay, so let's start with sample A. So we take sample A, and the first test we carry out, if we do this in a systematic way, it's going to make it easy. So I always start with a bromine water test. So I take about 1 centimeter of the sample, I add some bromine water, about the same amount, and I shake for 10 seconds. So I take the sample, add the bromine water, and shake. Now in this case, this orange color persisted, and 2 layers formed. So we've got 2 layers. We've got the orange layer at the bottom and the clear layer at the top. Sometimes a wee bit of the orange will transfer into the clear layer at the top. That won't matter. Okay, the second test that we always carry out is an acidified dichromate test. You could also use the acidified permanganate test, but I just advise you to stick to one. I use acidified dichromate. So I take the sample and I add 10 drops of, well, usually I add dichromate or potassium dichromate and then add the acid afterwards, but you might be just given acidified dichromate for a start, so you just add that. So your solution will go orange. You just shake it a wee bit, and then we have to place it into a hot water bath. So it's about 70 or 80 degrees Celsius. The warmer it is, the quicker you'll get any changes noticed. And we place it in there and we leave it for 5 minutes and we see if there's a color change. If the color goes green, We observed that, and in this case it did, so the color changed from orange to green. So now we know three things actually. We know that the bromine water didn't react. We noticed that there were 2 layers, and we've noticed that when we added dichromate to a new sample, it went from orange to green. Okay, and then we take a new sample again, a fresh sample of it, and we test it with damp litmus paper. So I add damp red litmus paper, stayed red. I add damp blue litmus paper, it stayed blue. What that means, the red didn't change, so it wasn't a base, it wasn't an amine. Okay, because amines is the only organic group we're looking at the moment, or an NH2 group that would cause it to go blue. And the blue one didn't go red, so it means the sample isn't a carboxylic acid. So that's all the observations we need. I've written down my observations here. This will be the first part of our report, would include what I have written down in the yellow here. The second part is justifying. So if you can remember, so the solution of the orange bromine water did not become colorless. That means that there was no carbon double bond carbon or no carbon triple bond carbon present. Now you could write that as there is no alkene or alkyne group present. Hence, the unknown sample, if we went back to the first page, can't be 5-amino-pent-2-ene, because that has a double bond. It can't be pent-2-ene-5-ol, as that also has a double bond. So remember, if the sample had a double bond, it would have changed color to colorless. So this formed 2 layers. Now what that means is that it's not going to be a small molecule with an alcohol, an amine, or a carboxylic acid group attached. So it can't be a molecule of 3 or less carbons with an OH, an NH2, or a COOH functional group. What that means, from the 6 samples we had earlier, it can't be ethanol, it can't be ethanoic acid either, because both of those molecules have only 2 carbons. Ethanol 2 carbons with an OH attached, and ethanoic acid 2 carbons with a carboxylic acid group attached, the C double bond OH. So the second test we did, remember, was we've actually eliminated 4 of the 6 things. So we've only got 2 left. And the 2 left that we have, if you could just go back to the start of the video and look again, we see that the 2 are pent-1-ol and pentanoic acid. So if we carry out the second test, we add our sample, we add acidified dichromate, and we heat. Now it went green. That is a positive test for an OH functional group. So we will say here there must be a primary or secondary OH functional group. So now we know, because we only had 2 left to choose from, pentanoic acid and pentanol, we know that this must be pentanol, because pentanoic acid would not change the solution, the color wouldn't change from orange to green. So just to confirm this, we go through and we do the final test, which is adding litmus paper. So we add both blue and damp blue and red litmus paper, and we just check that it doesn't change. It didn't change, so it means there's no amine group present, because the red litmus paper didn't go blue, and amine is a base, and there is no carboxylic acid present because the blue litmus didn't go red. Now we expected that, because we'd already decided, remember, that our molecule was pent-1-ol and not pentanoic acid, so we'd expected that we would have had a negative test for carboxylic acid. So now we can just say the molecule is pent-1-ol. We're pretty confident with this. So we've done most of the work we need to identify in this. Now we just have to write down the positive reaction that happened. There are 3 reactions that you might choose from. Either the addition reaction if you had a positive observation in your first test, an oxidation reaction if you had a positive observation in your second test, or an acid-base reaction if you added carbonate in the third test and you got a positive reaction there. In this case, we had the second test as a positive reaction, so we draw an oxidation reaction. And we should write down very clearly that this is an oxidation reaction and draw it. Now remember, if we have an alcohol and it's oxidized, a double bond carbon or a carbonyl group is joined to the carbon that has the OH here. So the last thing we need to do, so the two parts we've done so far for this report is the bulk of what we have to write. But the next thing we have to write is we actually have to look at the safety data. So here in the blue on the right, I've got the summary of the safety data. We've got the lethal dose of 2 grams per kilogram. And we've got some other information that this chemical pent-1-ol might cause irritation to skin and eyes. Overexposure might cause headaches, tiredness, nausea, and vomiting. So we're going to just give some advice on how we might use this safely in this cleaning solution. So the first thing I might say is I always like to say, well, we have to be aware that children might get hold of these things and use them. So if 2 grams is enough to kill someone, or lethal, every 2 grams for 1 kilogram, we can say that a 10 kilogram child would need 10 times as much. So I would go and say, well, 20 grams might be lethal for a 10 kilogram child. So you know what? The cleaning solution should be stored in a lock cupboard, and there should be a warning on it, harmful if swallowed. The other thing we could do is we could say the bottle must have a child-proof lock lid on the top, and again it might have on the label harmful if swallowed. You could also say something like, and I've written this here, there should be instructions on the bottle for users to wear gloves and eye protection to make sure they don't irritate their skin. Now, if you want excellence, you need to make sure you do this explanation thoroughly. You think carefully, some good solutions to how you might make these chemicals safe for people who are using them. Okay, so that's our first one. Okay, so let's have a look at our second sample that I had for this. Sample B. Okay, so the first thing I'm going to do is add bromine water to it. So here's sample B, add bromine water, shake. Notice here, I can't see 2 layers. There's only 1 layer and it's orange. So that's interesting. So we write down the orange color stayed, or the brown color, whatever, however strong your bromine water is, it's going to look either orange or brown. And there is only 1 layer, so there's not 2 layers. That means that whatever the sample was, it must be soluble, and I'm already thinking it's going to have 3 or less carbons and be an amine, a carboxylic acid, or an alcohol. So I take a fresh sample, and then I add my acidified dichromate. Remember, it's either going to be in a bottle that's already acidified, or you're going to have to add some dichromate and then some acid. And then I take it and I put it into my water bath. I leave it there for 5 minutes. Hey presto, stays orange. So we've had now 2 negative tests. Okay, so stays orange means there is no OH functional group in this molecule. Then we take a third sample and we add to the third sample. We take a bit of damp litmus paper and we test it with the red litmus paper, and then we test it with the blue. And the blue litmus paper actually turns red. Now at this point, if we ever have blue litmus paper turns red, we want to confirm this reaction. So we take the we take the litmus paper out of the sample and we squirt in some sodium carbonate solution. And if I put this solution into the test tube, we will get bubbles form. And these bubbles are actually carbon dioxide gas. So this is a positive test for an acid. So here we know it's carboxylic acid. So this is what we would write for our observation. And then on the next page here, I'm going to write. So let's see if we can explain or identify and explain what molecule this is. So remember, the bromine water did not go colorless when we shook it. So there's no carbon double bond carbon or carbon triple bond carbon. Hence, we can cross out here the 5-amino pent-2-ene, and we can cross out the pent-2-ene 5-ol. Because only 1 layer formed, it means it was soluble in water. So there must be either an OH, an NH2, or a carboxylic acid group, and it must be attached to 3 or less carbons. So the pent-1-ol is way too big. It's 5 carbons. That would be insoluble. and the pentanoic acid is too big as well. So we can cross those two out. So now we're left with just ethanoic acid and ethanol, our two possible unknown sample for sample B. So the next thing we do is we added the acidified dichromate. Remember, we heated it, it stayed orange. Now what that means is that if it didn't react for this acidified dichromate test, which is a test for an OH group, it means it can't be the alcohol. So it can't be ethanol. So it's going to be what's left, which is ethanoic acid. Now we're pretty sure it's ethanoic acid, but we're still going to carry out the fifth test to be sure. So we add blue litmus paper and it went pink. That's perfect. That is the test for an acid, but we're going to confirm this also. So we add sodium carbonate and we saw that bubbles were produced. So that confirms that the unknown molecule B, is actually ethanoic acid. Now, because we have to say what type of reaction this is. Because the ethanoic acid reacted with a carbonate, that's an acid-base reaction, and we have to draw it. So we draw ethanoic acid reacting with sodium carbonate. We get the sodium ethanoate, carbon dioxide, and water. So the last thing we do, remember, is we're going to be given the data on this. So we're given an LD50, or a lethal dose here, of 3 grams per every kilogram. So a 10 kilogram child is going to, we have to keep it away from ingesting 30 grams, right? So the first thing we might say is 30 grams might be lethal to a 10 kilogram child. So should be stored in a locked cupboard, or remember, we should be stored in a bottle with a child-proof lock, and a warning label, harmful if swallowed, should be printed on the bottle, because we don't want anybody taking a swallow or a drink of this. This is only 2 tablespoons, 2 dessert spoons full of liquid, right? So it doesn't take a lot for someone to die from this. There should also be instructions on the bottle for users to use gloves and eye protections, because here it says that ingestion can cause severe swelling, severe damage to the delicate tissue, and danger of perforation. That doesn't sound very nice, does it? But it also says causes severe burns. So we need to say something about the severe burns. But remember, for excellence, you just have to use your common sense. If you can do that bit of maths and say, well, this is how many grams it would be to be lethal, that's really good. But also talk about how you might prevent it using common sense. Think about how we normally do that with dangerous chemicals in the house, and then talk about what type of warning labels you might put on it. Okay, so let's look at our third sample. Sample 3, let's go through the observations here. So the first thing, again, we're going to do bromine water. So we add bromine water to our sample, we shake it, and boom, it goes colorless. Sometimes it goes white. This one went colorless, but we can also see there's 2 layers. So you can see there's 2 layers. We see that boundary layer or line between the 2 layers, so it's pretty obvious. We take a new sample, we're going to add the acidified dichromate. Remember, either as the dichromate acidified, or we add the dichromate with extra dilute acid. And we heat that in a water bath, 80 degrees Celsius, and it doesn't change. So we now have a sample that reacts with bromine water, doesn't react with acidified dichromate, and we'll just check it with our litmus paper. So we take the sample, we check it, damp litmus paper, oh, it goes blue. Well, there's only one of the functional groups we were looking at this level that it turns blue, and that's an amine. So that's quite good. That's going to help us definitively say which one it is. So remember, the third test we did here was add litmus, both pink litmus and blue litmus, and see if it changed color. Okay, so let's write this up now. So the first solution changed color from orange to colorless when we added it to the sample and shook it. So there must be a carbon double bond carbon or a carbon triple bond carbon. So if we look at these 6 molecules, it's either going to be 5-amino pent-2-ene, or it's going to be pent-2-ene-5-ol. So we know actually from the get-go which 2 it's going to be, and it's not going to be the others. Also, because there's 2 layers, we can just write this down. It's not the 2 smaller molecules with the OH or the carboxylic acid attached, because they would be soluble. Okay. Remember the next test we did is we added acidified dichromate. It didn't change color. That means that this molecule does not have an OH functional group. So remember that we said that it was either going to be aminopent-2-ene or pent-2-ene-5-ol. It can't be pent-2-ene-5-ol because that has an OH functional group off the last carbon. It's a primary alcohol, and it didn't react with acidified dichromate, so it can't be pent-2-ene-5-ol. It must be, and we can work this out by the second one, 5-aminopent-2-ene. Now I could just go through and do the last test. I wouldn't necessarily need to, but I would expect when I add the pink and the blue litmus paper, oh wait, let's have a look at this again. Oh, there is an amine group here. Okay, so there's two things happening on this one. So we do the last test. We add pink litmus and it went blue. That means that the amine functional group is present. But that's all right. That confirms that this is the molecule that is our third unknown sample, right? It is this 5-aminopent-2-ene. Remember, because it made the bromine water change color to colorless, and the pink litmus paper went blue. So the actual test, the reaction that happened here was the addition reaction with the bromine water, so we need to draw that one. So we start with our alkene with the double bond in the molecule here, and we show the hydrogens being added to it. Make sure you put the reagent in and make sure this is all done perfectly. To get the best marks, you need to have an accurate equation. So the last thing we're going to do again is look at the safety data. Here it says the lethal dose is quite small. It's 0.04 grams per kilogram, and it can cause skin burns and serious eye damage. So this it's quite a low dose for fatalities. So it's going to be a really, we have to be very careful if we put it in a solution that's going to be around people in everyday life if they're cleaning desks. So my suggestion here is we don't even put it in a solution, or if you make a solution up with it, it can only have a very small proportion of it to the total volume. There should be some instructions on the bottle telling people to use eye protection, right? And use gloves because it can cause burns and serious eye damage, right? And you go through and do this the same way. If we can always say, look, it's 4 grams that's lethal to a 10 kilogram child. And then that's why I can say, look, I don't think you should actually have this in the desk cleaner because it's such a small dose would kill somebody. I would recommend we don't even buy it or we don't use it. But I have to justify why I would recommend that, and that's because it's got such a low lethal dose. Okay, I hope this has been helpful. Good luck in preparation for this internal.
Okay, if you've got to this part of the video, you've obviously watched all the examples that I had on those 3 questions. Hopefully this has fortified your understanding of geometric isomers, and you are now well prepared to go and attack that exam. Good luck, and if you found this video useful, don't forget to like it, subscribe, and look out for new videos that I might put up by clicking that bell. See you later.